Okay, so let's, before we get to calculate the R set or get a sense of how people move in a building, let's look at the problem of the fire growth. Okay, so the bottom line is that if we understand how fire grows, then we can make decisions of how to simplify it. Is that okay? The problem with using the approach of getting an experiential result is that it doesn't really have any relationship to the physics. So the moment it doesn't have any relationship to the physics, you have no idea how far you can extrapolate that number. And what worked for that particular theory under those particular conditions, while we are applying it in a generalized way, doesn't necessarily mean that it's going to work everywhere. Is that okay? So let's start the simple way. Okay, so we've talked about ignition. We know it's going to happen. We know we're going to have a fuel, and we know we have to make decisions on how to model that fuel. So let's simplify the problem to its minimum, okay? And let's just simply take a problem of a piece of fuel. Okay, so that's your piece of fuel. And let's try to identify what are the processes, okay? So I am going to take my piece of fuel and I'm going to ignite it in the center. Okay, so I have put a hot spot in there and I actually got ignition in that point. Now, what is the chain of events that now I'm going to create?
I'm going to start by the hot spot growing and enveloping the whole.
Okay, so effectively it's going to start growing, and at some point we'll cover the entire area of the fuel. Okay? Now, how do I establish how fast it's going to grow? Because effectively, as you remember well, this is a race against time. Is that okay? So I need to be able to establish what is going to happen. Okay? Now, before I get to the time, how big can that fire get?
The size of the cushion.
Yeah.
I was going to, just say limited by the mass flux of the fuel.
Okay, so in size, it's never going to be bigger than A. Is that okay? Do we agree? So how much fuel is going to be produced? There's going to be a burning rate. Is that okay? So there's some fuel that is going to be generated, and that burning rate per unit area multiplied by the area will give me the amount of fuel that is produced. Are we happy with that? So if I define the burning rate, okay, this is in kilograms per meter squared per second. Okay, the rate of fuel that I'm being produced per second. The area defined in meters squared, so I can establish the amount of fuel that is being produced as being the maximum, the area multiplied by the burning rate. Are we happy with that? Okay, so that is going to give me kilograms per second of fuel. So on that basis, how much energy is going to be produced? Or the heat of combustion, no? So basically, I'm multiplying it by the heat of combustion. So I get the heat of combustion, and that is going to be in joules per kilogram of fuel. Okay? So my heat release rate is going to be the area times the burning rate per unit area times the heat of combustion. Okay? Kilograms cancels with kilograms, joules per second, watts. Are we happy with that? So in time, This is my heat release rate. This is my time. And I know what the maximum value is there. So this is Q max. Is everybody comfortable with that? Yeah, pretty straightforward, no? So, I know what the end point is. How do I go from 0 there to there? At the ignition point, it's 0 area. So this is 0. So this is 0. So this is my starting point. This is ignition. And now I need to be able to go there. Yes?
Do you then like imagine like a flame spread model to carry, to then populate the...
Okay, so effectively I need to spread, no? Because it starts in a point and it's going to grow, as you were explaining. So it's a flame spread model. Okay, so what is that flame spread model? What has to happen for the flame to spread?
Heat transfer to a further area.
Okay, so effectively I'm going to now look at it from the side. So here's my fuel. This is my ignition point. And a little flame starts establishing it in here. And there's going to be heat transfer. Here's a heat flux heating up a certain area, small a, okay, until it brings it to what?
It's the ignition temperature.
Okay, so you're going to call it ignition temperature. Okay? What is effectively an ignition temperature? Hmm?
Is it like the point where you have like a local energy balance that's basically positive, where now like the endothermic processes of pyrolysis and the gas phase reactions?
Okay, let's split it, okay? So we're going to have endothermic processes. So here in the solid, I'm going to have two things that are happening. One, I need to increase its enthalpy. Is that okay? So it's starting at T ambient, okay? And I have to start increasing the enthalpy of the solid. Is that okay? And at the same time, I'm going to have endothermic processes, which is a chemical degradation. And these endothermic processes are going to have a heat of pyrolysis. Is that okay? So effectively, it starts at T ambient, and somehow the temperature starts growing in. So it starts at the beginning at T ambient, and then the temperature starts growing like this. Are we happy with that? Until at some point, you heat up a temperature that you're calling T ignition. Yep.
Where the concentration of pyrolysis gases is high enough for further flame propagation?
We haven't got there, but yes, at some point you have to create a flammable mixture. So then we get into the gas phase. We're still in the solid phase. What is the concept of an ignition temperature? Okay, let's go back to the basics. What describes an endothermic pyrolysis reaction? Give me a mathematical formula that will describe an endothermic pyrolysis reaction. Okay, it's an Arrhenius. So basically you're going to have some pre-exponential constant. Okay? You're going to have an e to the minus e over RT. Okay? This is the activation energy, the universal gas constant, the temperature. Okay? And for most chemical reactions, you will have the concentrations of the reactants. Is that okay? Now, in this particular case, it's a bit tricky, no? Because what are the reactants?
It's the material itself. So
Yes.
it's just the first order reaction.
Okay? So, if I'm going to have my reaction rate, what am I consuming?
Pyrolysis gases you already assuming.
No, I'm not gasifying yet. I'm still getting there. I'm still in the solid.
You're consuming the temperature, the enthalpy difference between your temperature and
So-
the temperature at which the pyrolysis occurs.
I'm giving energy to the solid.
Right.
I'm elevating its temperature, as I can see here, so the enthalpy is increasing. Is that okay? But at the same time, at some point, I start activating these reactions. Okay? And those reactions are going to break down the solid. Are we comfortable with that? Okay, so this, I'm happy. What kind of order is this reaction? What is the chemistry?
I'd say it's first order because the rate of evolution of material is simply proportional to the solid you have to start with.
Okay?
So I would say it's first order. It doesn't rely on two reactants interacting.
No. It doesn't. Potentially it doesn't, no? So that would be an endothermic inert pyrolysis.
Right.
You're inside, you're assuming diffusion is negligible. Okay, so it's not oxygen activated, although sometimes it is, in which case you will have to have both. So effectively you're going to have here some mass of the fuel. Is that okay? Are we happy with that? Or should I put just a concentration? Does it matter? So, of all of you, which ones of you went to the morning sessions on chemical kinetics? You haven't learned anything? What should I be writing?
You should write the concentration if it's a first order reaction.
Yeah, but what is the concentration in a solid? Let's change it.
The density.
You're assuming a reaction in the solid phase, right? We just said it has to, we need to have pyrolysis. So this concentration will be the concentration of gases that already had formed and are burning within the flame.
No. I'm still in the solid. The flame is here.
Yes, but what's producing the energy from combustion is the...
No. I'm assuming the energy is coming in. So imagine I'm heating with a radiant panel. Okay, so forget about the combustion. We'll get there. We haven't got that far. Okay, we're still in the solid. I'm trying to degrade the solid, and I want to have an expression. So if I have the combustion of methane, okay, and I say a reduced chemistry of a single step, you will all give me the equation. Okay? Is that okay? Now I want to do the same thing, but for the solid.
It depends on the thickness that is engaged in pyrolysis.
It's a continuous system, so there's no thickness. Basically, I'm assuming that this is going deep. So effectively, the temperature is decreasing. This is a continuous function. So you will have degradation at all levels. The problem is that if this is high activation, then effectively your reaction rate, okay, at some sort of critical value, damp color critical number, the reaction is going to do this. Is that okay? High activation energy chemistry. Do I have a high activation energy reaction in the pyrolysis?
Yes, you have to heat up the solid.
Hmm?
Yes, you have to heat up the solid until...
No, you have to heat it, but is it high activation? Is this value a very large number? So if you treat this problem, okay, the appropriate way, so basically what you have is that E over R is this critical temperature. This is a non-dimensional temperature that basically is Tc over T, okay? And a high activation energy has a very big E, so this number is actually big, but because it has a very big E, the function goes 0, 0, 0, and then takes off very rapidly. That's a high activation energy reaction. A low activation energy reaction has actually a very small number. So this number is actually small. And what happens is that the equation just goes like this. Okay, so you're basically producing at a very sort of incremental rate, as opposed to having a critical value. Okay? So are pyrolysis reactions high activation? Yeah, most of them are. This is why we use a surrogate. This is why we can talk about an ignition temperature. Is that okay? Because effectively that ignition temperature is that critical value that makes a reaction take off. Is that okay? And you know that if you're past that number, you're producing sufficient fuel that you can create a flammable mixture in the gas phase, and then that flammable mixture can be ignited by this kernel of the flame, and then you can progress to the next level. Is that clear? Yeah? So there is no such a thing as an ignition temperature. It is basically a surrogate that comes from the acceptance that this is a high activation energy. And therefore, you're very close when you fix this number and you call it an ignition temperature. Yes?
So that means we cannot use the same term for like low activation pyrolysis.
If you have a low activation energy, you will not have an ignition temperature. Effectively, it is a function that grows very slowly, and there is no such a thing as a radical change between on and off. Okay? Any questions? Do you have any questions? No? Okay, so then how thick is the layer that is pyrolyzing? We've assumed that it's a high activation energy reaction. Yep.
Would this now be based on heat transfer? Yeah.
Would it be? Well, that's what I'm asking.
I guess
This is the thermal thickness of the material, right?
Why? You just told me it's a high activation energy reaction.
so wouldn't that make it infinitely small then?
Exactly. Because the moment that you go to a temperature that is slightly lower, then what happens? Your reaction rate goes to 0. Are we happy with that? So can I assume that the reaction then is a surface reaction? Are we happy with that? And how much is coming out? Hmm? No. How much is coming out? What determines? Now it is a heat transfer problem, but what determines it?
Sorry, we say how much is coming
How much fuel is being produced? Who determines that?
That's going to be from that expression, because that's going to be the rate of degradation.
Yeah, but it's going to go to infinity. Who truncates that expression?
The heat generated by the flame.
Not the heat generated by the flame, but the heat transferred by the flame. So is the amount of energy that you are delivering, okay, that determines how much fuel you're producing. So effectively, all you're saying is, if I am delivering this amount of energy, okay, from the flame, okay, then effectively this has to be equal to the heat of pyrolysis times the burning rate. Tell me if you agree. Joules per kilogram, kilograms per meter squared per second. Kilograms cancel out, joules per meter squared over second gives me watts per meter squared. Watts per meter squared. At least the units are okay.
We're assuming no losses, right?
Of course. You can add the losses later. Okay, at this point we're assuming that all the energy is coming from the flame and is heating up the material and producing the fuel. Is that okay? Yeah? So do I need the chemistry? Do I even have to consider the fact that this is a chemical reaction?
Sorry, how does the Q flux define here?
No, that's in the gas phase. Combustion is chemistry. That part I'm okay.
Oh, okay.
We're talking about the solid.
Okay, so I
Pre-exponential
guess
factor.
vacuum.
Huh?
You need to know the pre-exponential factor
For what purpose?
to know how much yield.
But I don't need it because I'm just saying that this is defined by how much energy the flame is giving me.
It's just a radiant heat transfer.
Yeah. So do I need to address the pyrolysis?
No, once you have the heat of pyrolysis, then you can get the mass flux.
So the only manifestation of the chemistry then is the heat of pyrolysis? Huh? Well, but that's later. You keep going to the gas phase. We'll get later there. I'm just in the solid yet. I mean, don't rush me. I have to fill 3 hours. You know, I need to talk. So we're still in the solid. So, no, seriously, do I need the chemistry?
Assuming that it's is it a non-gyro material? It's a material that doesn't change its chemistry?
Well, it's pyrolyzing. It needs heat to change its chemistry. But the question is, if I want to calculate how much fuel do I have, do I need the chemistry?
No, you don't know. You already know that it's a high activation energy, so you don't need the chemistry.
Yeah. So basically, the only thing that you need is the fact that you need to understand that it's a high activation energy problem, which effectively makes it a surface problem, which effectively makes it an energy balance at the surface. Is that okay? Yep.
So this is a high activation energy process, but we can supply the heat at twice the critical temperature or 3 times the critical temperature.
You can't. Because the moment that you exceed in 1 degree this, your reaction rate goes so high that the limiting factor becomes the supply. So the temperature will never go above the energy of the critical temperature. Because it's limited by the supply of energy. So you understand where I'm getting to. So effectively, I just created the first simplified flame spread model. Because effectively, what I need is a 2-stage process. What is the first stage? I have to bring the temperature from the ambient temperature to the critical temperature, which I'm going to be calling an ignition temperature. Okay? So effectively, I need to get mCp T ignition minus T infinity. That's the enthalpy. Is that okay? Once I get there, it starts gasifying and is limited by the energy supply that I have. Okay, that gives me the burning rate. And on the basis of the burning rate, then now I can combust. Okay? And once you combust, you will have the heat flux and then it closes the loop. Is that okay? That's the process. Now, so then why do people spend so much time creating pyrolysis models?
Care about what product species
That will imply that you understand the decomposition chemistry. Okay? And why would you care about it? So why would you care about the composition of the fuel that is coming out? Let's not get there yet, please, okay? In principle, let's make the assumption that people should not be in the same place as smoke, okay? The moment that you accept that toxicity is an issue in fire, you've lowered the bar. because you're accepting that people will be exposed to smoke. And that's really, nowadays everybody talks about toxicity. This is a big drama. You know, if you have polyisocyanurate, then produces HCN. I don't care. My bar is people should not be exposed to smoke. So what do I care what's in the smoke? The moment I accept that there's toxics in the smoke, I have accepted that the bar has been lowered. Okay, I'm not willing to get there. So that's not toxicity. Why do I care what the composition chemistry is of the gases?
Because that's where you get the combustion.
Only as a function of the combustion, no? So if I can model the combustion chemistry, and that allows me to get a more precise version of this, then effectively I'm okay. Then yes, because effectively you want to know what the composition is, so that composition then is fed into a chemical kinetics model in the combustion phase, and then eventually that gives you back a heat flux. Are we happy with that? Do we have the capacity to do that with this type of products? Is there any combustion chemistry model that has the capacity to resolve this type of chemicals? What do you think is a typical combustion model that we use in a CFD calculation for fire?
Probably just gasified fuel plus air,
Yes?
I would guess.
We don't even do that.
Okay.
Yeah, so all we do is basically we assume the location, okay, where you have a stoichiometric mixture. So you do a mixed refraction type of model where you have no combustion chemistry in the gas phase. All the reaction terms disappear. And then what you do is you have a heat of combustion that is an average bulk value. And you release the energy in that place, and the rate of energy release is defined by the supply of fuel and the supply of oxidizer, not by its chemistry. So we never solve the chemistry.
So straight diffusion flame.
It's a straight diffusion flame, Burke-Schumann. So we don't do more than Burke-Schumann. And the reason is because what comes out of these materials is extraordinarily complex. So effectively, you don't need any of this stuff. At the end, if you really want to model the problem, you are going to get this in a very simple way, and then you're going to implement it in a very simple way. Okay? And that's what you're going to use to basically spread the reaction. Okay? So what would be the most simple of manners? So let's say now we understand we have to heat this up until we get to the ignition temperature, high activation energy, and then we are producing energy that then we're going to be inputting in a CFD model that is going to give me the heat flux, and then effectively that brings it back to this point. Okay? Is there a simpler way to do it? Well, let's try. I want to be able to calculate my flame spread.
Flame temperature and then like some sort of black body radiation from an assumed area.
So you can estimate a flame temperature. So if you go to a paper by Foreman Williams in 1972, he estimated that these diffusion flames, given the energy balance that you have an average temperature of about 1400 degrees Kelvin.
Fahrenheit.
Kelvin.
Kelvin.
Okay? He did put all these theoretical arguments, and it's basically the temperature of a diffusion flame, and he said plus minus a few degrees. If you put 1400, you can put an emissivity of the flame, and on the basis of that you can calculate a radiative heat flux. Okay? So if I have a radiative heat flux from the flame, then can I simplify this problem further? Yeah, so if I now have the Q, so effectively now I have this value. It's done. Okay? What will be the next step of the simplification? Yes? Yeah, do I need the heat of pyrolysis anymore?
No, because that's been pulled into your analysis that gave you the 1400K.
Exactly, because effectively the only reason why I needed the fuel was to feed in into my CFD so I could actually get the Q. But if I already found a mechanism to estimate the Q, then I don't need anymore this equation because I don't need to know how much fuel is burning. All I need to know is that I reached the ignition temperature. Are we happy? So in the period in which your solid goes from T infinity, okay, to T ignition, do I have any heat sinks beyond the increase in enthalpy? As it's heating up from ambient to that T ignition, yeah, it's part of the enthalpy, no? So effectively, I'm providing heat, and the heat is creating this curve, and the fact that this curve has a gradient is effectively sending heat inwards. It's not really heat losses. I could actually make an energy balance here and have heat losses from the surface, but I will balance all this out in this net value. Is that okay? But I'm talking about the solid. Do I have any heat sinks in the solid? Beyond the fact that I'm transferring heat into the solid. Pyrolysis. Do I have pyrolysis at temperatures below T ignition?
No, because we've already assumed it's the...
Exactly. So you already assumed that it's high activation, so there's nothing here. So I can assume now that it's an inert solid. Is that okay? And all I'm doing is attaining a change from T infinity to T ignition. Are we okay with that?
Are we going to have change of a state from solid to liquid also?
Well, you can have a material that melts, in which case, yes, you will have to add a heat sink from the phase change. Okay? You can have a material that, for example, in the case of timber, that has moisture, in which case you will have to dry the material, and you can add a heat sink for that. Is that okay? So you can actually add the heat sinks if, depending on the type of fuel that you have. Okay? But in principle, those will be add-ons to the problem. I can do exactly the same thing, still treat it as inert heating, but effectively take the moisture content, okay, multiply it by the heat of vaporization of water, and make that sink energy that needs to be overcome before I can get to T ignition. Okay, so that will be easy. In the case of melting, it's the same, because melting is going to happen before it reaches T ignition. So effectively, you're going to put a heat sink that sucks energy, so you have to overcome the melting and then heat it up to ignition. So it's just simply adding a heat sink. Is that okay? So potentially melting and moisture are fundamentally heat sinks.
But then too, the enthalpy of fusion is usually a lot less than the enthalpy of vaporization.
Yes.
So it won't change it very much.
No, it generally doesn't, while water does.
Yeah.
So moisture is very high. So with moisture, you get these plateaus before you go up.
But that's the enthalpy of vaporization. That's a big thing with water.
Yeah,
Okay.
yeah. Yeah, that's why, because the vaporization of water happens at 100 degrees. You know, it happens much earlier than the T ignition, and that's why it is a big sink. Okay? But are we comfortable with that? So effectively, I have summarized my problem into establishing an estimate of this number that takes into account combustion is radiation, all the components, and summarize it into some sort of estimate of the flame heat flux. That estimate then allows me to heat up the solid in an inert manner in such a way that I can bring its temperature to its ignition temperature. The manifestations of the chemistry appear here. Okay? And here is the combustion. So when it comes to flame spread, not only I have eliminated the chemistry of the problem, but I've also eliminated combustion. What I'm dealing with is a radiant panel that is igniting an inert solid. Is that okay? Now you can go home. So as you can see, we are constantly eliminating combustion from the problem. Constantly. Because in the case of fire, it is too complicated. So where does combustion come when you're dealing with fire? It's in the efforts that we make to eliminate it. And eliminate it in an appropriate manner. Because the moment that we actually have to resolve the combustion, what do we have to do? We have to resolve a combustion chemistry that is extremely complex, okay, mixed with a problem of fluid mechanics that is extremely complex, with a supply of fuel that is extremely complex. So the efforts that we put in understanding combustion are not because we want to model combustion, but because we want to eliminate it in an effective way. So at the end, if we want to have a practical solution to the problem, what we're going to do is effectively eliminate the combustion problem completely, but in a way that I know represents appropriately, okay, what I need to obtain from these equations. Is that clear? So a lot of the efforts that we do are fundamentally understanding pyrolysis, understanding combustion, understanding all these different things, means of heat transfer, in such a way that we can narrow it down to a much simpler problem that is tractable. Once you have a simpler problem that is tractable, then I can actually calculate a time that it takes me to heat this up. So if I take now a semi-infinite solid, and I apply this heat flux to the semi-infinite solid, you know, I only have to take in Cropera and DeWitt or any of these heat transfer books, and I can calculate the time that it takes for the temperature to reach the ignition temperature at the surface. Is that okay? And that effectively is the surrogate for the entire pyrolysis process. Okay? So what I'm going to be doing now is, by doing this, what I do is I take my inert heating, and what am I going to get here? A time to ignition. Is that okay? So now, in that time to ignition, I am going to heat up this area here. So I'm going to have a characteristic length scale that is being heated by the flame, and it's going to take me this long to ignite it. So now, if I divide that characteristic length scale by the time to ignition, I get my flame spread velocity. Is that okay? Conceptually, it's fine. The problem is, what is that characteristic length scale? So I have to characterize what distance is being heated, no? Yeah. So now let's think of this, okay? Here's my solid, okay? And I ignite it in the bottom. If there wasn't carpet here, I would do an experiment, but unfortunately that would be a little bit problematic. But imagine if I ignite in the bottom, and the flame actually spreads like this. So then the flame length becomes more or less my heating area, no? Or my heating length. Is that clear? And it's going to be fairly long. So this number is big, so my flame spread velocity is big. Now let's change the problem. And I ignite in the top. And now your flame goes up, and now you have only a very thin area that is being heated because of radiation from the flame going towards the solid. Then you have a very tiny surface area. Is that okay? And then this is very small, and therefore the flame spread velocity is very small. If I put it horizontal, then I get a flame, and that flame is going to cover an intermediate area. It's not as big as this one, it's not as small as this one, but it's somewhere in between, so I get an intermediate flame spread velocity. So depending on the geometry, for example, I will actually change the problem. How do I determine what that value is? Yep.
This is assuming no flow velocity, right?
Well, yeah, I'm assuming that let's assume there's no flow, okay? I could add the flow and then I get an even more complicated problem. But how do I resolve this?
The view factor?
Huh?
The view factor? Like,
Yes, but how do I know how big the flame is?
you don't know the shape, so
We can assess where we have combustible materials and
But how do you do that if I already eliminated all the chemistry? I don't have any more burning rate and anything.
Want some experiments?
Hmm?
Want some experiments?
Well, like 2.5 minutes, huh?
Could you just estimate it from the heat flux, like divided by the area of the flame?
Yeah, but how do you get the area of the flame?
Just try the small surface and just keep increasing the change.
Well, but it's going to grow linearly because LC is proportional to VS. So the bigger I make the length, the faster it's going to spread. So you see, once again, what do I have to do? I have to try to find a way to establish the combustion so I can get an estimate that allows me to eliminate the combustion. Is that okay? So this is constantly the game. You introduce the problem, you find a way to get yourself out of it, and then you eliminate the problem. Okay? Effectively, we're going to come up with some sort of preheating length. So there's a paper by Chen and Tien many years ago, and basically this is, just to give you an example, this is a flame, okay? And they had a force flow velocity in this particular case, okay? And they basically said that here is my flame, I know the temperature, so I know the heat flux going in this direction, okay? So what they said is that the heating length, okay, has to be the place where you balance the energy that you need to heat up the air by the energy that you need to heat up, that is produced by the flame. Is that okay? So effectively, if you multiply this by the density of the air times the specific heat, okay, and the temperature increase from ambient to the temperature of the flame, and you make it equal to this Q double prime, so Q flame going in this direction has to be equal to the velocity times the density times the specific heat times T flame minus T infinity. Is that okay? And the moment these two are equal, okay, then effectively you get a characteristic length scale. So they approximate this term by saying that it's K of the air times T flame minus T infinity over a characteristic length scale. So basically they're saying that this is heat conduction going forwards, while this is the advection going in the opposite direction. Okay? So all of a sudden, what we've done is say, okay, fair enough, the temperatures go away. Okay? And this is rho Cp divided, so UK of the air divided by rho of the air times Cp of the air. The length K goes in here, and the velocity goes underneath. So this becomes alpha over U infinity. Is that okay?
And then I guess the idea now, going back to your problem, is that that U can be a function of, like now you can have a buoyancy.
Of course, you can change this for a buoyant velocity if you put it vertical.
Exactly, and then that's how you're going to get your new characteristic length.
Yes. Okay, so effectively, Chen and Tien said the characteristic length scale is alpha of the air divided by U infinity. Okay, meters squared over second divided by meters per second gives you length. Is that okay? Now, what is the fundamental physical condition that needs to be met for this analysis to be valid? Effectively, what Tien and Chen argued is if this equilibrium doesn't happen, okay, and this velocity is bigger than the equilibrium, then what happens? The flame gets cooled off. That's blow off. Okay, so this balance has to exist because otherwise you blow off the flame. So it has a physical meaning. While the flame exists, the heat forward by the flame has to be equal to the energy pushed back by the flow. The moment this imbalance doesn't happen, okay, then what happens? Effectively, the flame blows off. If I reduce the velocity, then what happens? The length scale becomes bigger. Okay? Because I can heat it very rapidly, so I can heat it very far. The conduction pushes very far. But if I fail this equality, then the flame is blown off. Okay? And that's an extinction condition, and then you have no flame. Pretty smart, no? So there you have a mechanism by which I determine this, and with that I can calculate the opposed flame spread velocity. Yes?
But you don't know the shape of your object that's burning. So if like flame travels faster upward, so if there's an angle to that problem, which we can't know.
Well, let me put it this way. If it's an angle, if it's a plate, and I start changing the angle, then it's what you were saying. So then I have to use, for example, buoyancy. And then I will have to come up, with a way. So there's a subsequent paper that comes from this, which is for natural convection, where effectively they look at the flame spread in different angles, and they create a Grashof over Reynolds number equivalent that basically is a mixed flow solution, where you have partially the U infinity, which is a force flow, and partially buoyancy, depending on the angle, and the gravity vector, effectively you have G times the sine of the angle.
Right, but in a room, you don't have one-shaped items. You have various shapes.
Why do you want to complicate my life? Okay? Of course, we're simplifying the problem. I just made it a square. Okay? It's already complicated enough. Of course, if you have a geometry that is complex, you cannot avoid the CFD. But the concept is the same. Is that okay? So effectively, you're still creating the same thing, but then you are dominated by a very complex CFD solution that effectively gives you what the flow field is. But conceptually, it cannot change because otherwise you blow off the flame. So that balance of energy that Chen and Tien postulated effectively is telling you the mechanism by which you establish what the characteristic length scale is. In the case of a opposed flow. How would you do it for forward when actually the two of them are in the same direction? In other words, the other length scale. So if the flame now is like this, and this is the part that is pyrolyzing, and this is the part that is preheating. Okay? And you need to know this is now my characteristic length scale. So in that case, it's not a blow-off problem. Because the more I blow, the longer it's going to get. So what is the criteria there? I mean, you could potentially do a boundary layer solution, no? And effectively calculate it for a boundary layer and find what the flame length is going to be. And as a function of that, find this. And what will be the criteria? Well, how do you know the flame has ended?
What has ended?
The flame. How do you know the flame is finished?
That there is no more heat being released.
Okay, and when is that going to happen?
It mixed with air.
So,
We just lose that ratio at some point and just end the flame.
okay, so, but think about it. So you are producing fuel, air is coming in, think of the boundary layer problem. So air is coming in, you're producing fuel, the two of them start burning. When does a reaction die? With an infinite chemistry, when is it going to happen?
Fuel is exhausted.
Let him talk. Exactly. Okay, Burke-Schumann. Is that okay? So the criteria is total fuel consumption. And that gives you the flame length. Now, obviously, if the chemistry dies before, because you have too much stretch, like in the case of the smoke point, then the flame is going to be a bit shorter. But we make the assumption of infinite chemistry, and we say, well, let's forget about the chemistry, it's strong enough, and if we make a mistake, well, we make a mistake for a little while, but it's conservative because total fuel consumption represents the longest possible flame I can have. So when you have forward, the criteria is always going to be total fuel consumption. And I will find ways by which I can calculate a simple flame length. Okay? In some cases, it's purely an empirical correlation. In other cases, it will be a boundary layer type of analysis, like the Emmons problem. So Howard Emmons, do you know who Howard Emmons is?
He was my advisor.
Oh. Well, so we're related. You know, he was my advisor's postdoc advisor. And it's all in the family. So Howard Emmons was one of the most prominent fire scientists in the 1950s, and in 1956, he published this paper that effectively he analyzed the solution to the boundary layer problem. Okay? And the solution to the boundary layer problem effectively established that the burning rate is proportional to the shear at the surface. Okay? And that led to the concept of extending Spaulding's B number, or the mass transfer number, into boundary layers. Years later, Packney and Shee, developed a solution by which they calculated the burning, the shape of the flame, and the point of total fuel consumption with which they could actually calculate a flame length. They took Emmons' problem and they extended it. In between, there's everybody that has a name in combustion did something trying to get there, and they didn't. So there's Foreman Williams, Irving Glassman, Anna Malai, Sibulkin, you name it. Everybody in the 70s tried that problem until eventually Packney and Shee came up with the flame length. Okay, so that was the boundary layer. Everything more complicated than that, CFD. Okay, but effectively you have to come up with a way in which you establish the flame length. Is that okay? And that becomes the criteria that enables me to establish what the characteristic length scale is. Is that okay? So now I have my flame spread. Okay? And the flame spread, effectively, I can assume if this is horizontal, okay? It's not a complex chair, okay? It starts spreading in this direction, no? Are we happy with that? And that allows me to establish what is going to be the burning area. Is that okay? Yep. So if this is the radius is going to be the flame spread velocity times time. And the area is going to be pi r squared, so it's going to be Vs squared times squared. Is that okay? Pi. Sorry. Is that okay? Yep. So now I know what my area is. So now Q of T as a function of time becomes the area, which is pi Vs squared T squared times the burning rate times the heat of combustion. Okay? And then I say, well, constant, 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 constant. I take all this and I call it alpha T squared. You seem all to be shocked. So now that I have a very simple problem, I can say, here's my fire. And once it gets to here, the burning rate is a constant. So Qmax is a constant until I consume the fuel. Time to burnout, in which case flame dies. Are you all happy with that? Yeah.
Sorry, do you find that in time, like by integrating this curve, based on the amount of fuel that you have to burn?
Yeah, of course. I mean, because basically I'm burning fuel at a certain rate.
Yeah.
Okay? So at some point I would have burned the whole thing, and effectively that's the point where is a burnout. Is that okay? Are you all happy with that? So where does this, so the alpha T squared is embedded in the codes. So what people do is they say, well, given typical type of furniture, typical type of materials, this is the alpha that we should expect. They assume that the fire starts in the middle of the room and it grows radially. And as a function of that, you can create a fire. Now, as you can see, I have employed combustion principles at all levels. Okay? But the way I have employed those combustion principles are fundamentally directed towards eliminating combustion from the problem. Because this is not a combustion problem anymore. Okay? It's an oversimplified representation of an event where all the combustion has been already sucked into a series of very basic concepts. But if you really think about it, all of a sudden, I have applied in this process, okay, the whole concept of extinction of Lignan. So effectively, this is a critical damp color number problem that allows me to get the value of a characteristic length scale. Okay? I have applied all sorts of concepts of degradation chemistry that have allowed me to eliminate the degradation chemistry from the problem. Is that okay? So as you're progressing, what you're doing is you're eliminating all the different things that one, represent uncertainty, and two, represent the complexity of the problem. Okay, and by doing so, I'm landing on something that is consistent with the accuracy of the other problem that I need to solve, which is the required safe egress time. There is absolutely no point for me to resolve pyrolysis to the endless detail if at the end I'm going to compare it to a completely arbitrary number. Is that okay? There is absolutely no need for me to do computational fluid dynamics to calculate the critical damp color number if this surrogate of an energy balance is sufficient to give me something that is consistent with this number. Yes?
Sorry, one of the reasons for that is because when we go back to how people are going to react, the error bars there are so large that we're completely comfortable in this context having an order of magnitude or something like that kind of estimate.
Yes, so long is fundamentally based on the appropriate principles. Okay, why? Because that enables me to say that I have to switch from a damp color criteria to a total fuel consumption criteria. Okay? It enables me to say that I don't have to worry about pyrolysis because it's a high activation energy. But if I put all these fire retardants that are going to change the pyrolysis chemistry and make it a low activation energy reaction, then I cannot use this simplification. So if I don't understand the principles I'm playing with, then I do not understand what my simplifications mean. Okay? And I might end up with an oversimplified solution that does not represent the problem. That's the essence of it. Is that okay? So understanding the concepts, okay, enables you to simplify the problem. And that many times is infinitely more complex than doing the brute force of just putting incredibly complex numerical solutions. Okay? And incredibly complex numerical solutions will have a million tweaking parameters, and clearly they're not necessarily going to be even more robust. And the one thing that is most important, they're going to be completely inconsistent with the precision of the other problem. Okay? So I'm killing myself running a CFD for an entire week, when in reality I'm going to compare it, you know, to 25 seconds plus minus 20, which is pointless. Okay? So the reason for doing all this, and the reason for doing it by hand, as opposed to showing it to you as a PowerPoint, is because basically what I've been doing is responding to what you were telling me. And as a function of that, I just created out of thin air a solution that actually was all based on combustion principles, but nevertheless had only one objective, which is simplify it to the minimum common denominator. I knew where I wanted to get, okay? But you told me how to get there. Is that okay? And you now understand the games that we're playing. So as we progress, you're going to see how I'm going to keep using ways by which I simplify the problem to try to deliver something that is consistent with the complexity and the precision of what we're doing. Okay? So let's take a 10-minute break, and then we'll finish up the class.